All right, so my goal for today is to wrap up bipolar junction transistor related things so that we can get into MOSFETs when we get back from the Martin Luther King Jr. holiday. So just reminding you all, we do not have class on Monday. But anyway. So what we're going to talk about here first is we're going to finish up our section on NPN amplifier biasing. And then we're going to talk about what happens when we have a PNP BJT. I don't really have any plans per se to go over PNP BJT biasing, and you'll see why. It's pretty darn simple. But if you want me to look at a couple of things, we should do that. So I believe we had finished up resistive divider biasing, and we're going to start looking at what is commonly called either emitter degeneration biasing or the four resistor bias network. So let's put that. Oh, good Lord. Does not look like two T's. So I'll draw a picture of it here, and then we'll talk a little bit about what degeneration means. So here is our collector resistance, RC. Here's our supply voltage, VCC. And then over here, we have our BJT. And normally the emitter terminal of our BJT has been tied directly to ground, but instead we're going to replace an emitter resistance RE between the emitter and ground, like so. And the practice of placing a resistor between the emitter terminal and ground is what's called emitter degeneration. What emitter degeneration does is it effectively minimizes the error that you would see in the DC bias operating point of the circuit. So effectively, if we have any variation in our supply voltages or any variation in our resistors R1 and R2, which I should probably draw, what we'll see is that the amount of change in those quantities when we have emitter degeneration results in a smaller change in our base emitter voltage and a smaller change in our collector current than if that resistor were not there. Okay. Another thing that emitter degeneration does, and we'll see this when we look at amplifiers in particular, is that it's going to boost the output impedance of an amplifier circuit at the cost of lowering the voltage gain of the amplifier circuit. So when we talk about these from a small signal perspective, we're going to see that including RE has both positive effects and negative effects. And so we have to figure out kind of how to balance things out. And sometimes we're going to do weird things like split our degeneration resistance up into two resistors so that we can only use part of it for the AC signal, but all of it for the DC signal, and all kinds of neat and weird things like that. Okay. All right. So let me identify all of our currents and all of that kind of jazz. So here's our base current, IB, our collector current, IC, and our emitter current, IE. Here is our voltage drop, VBE. And here is our voltage drop, VCE. And much like we did when we were looking at the resistive divider biasing network, we're going to replace everything to the left-hand side of the circuit with its Thevenin equivalent. Excuse me. So For analysis's sake, we're going to be looking at the following circuit. So here's VCC, RC, RE, RTH, and VTH, where our Thevenin voltage should just be VCC times R2 over R1 plus R2. Yet again, exact same situation as we had for the resistive divider biasing, so nothing should change because the left-hand side of the circuit didn't change. And our Thevenin resistance should be R1 in parallel with R2 yet again. And now I'll go through and identify my currents and all that kind of jazz. So IB, IC, IE, VBE, and VCE like so. All right, so now using this simplified version over here on the right-hand side, we are going to figure out how everything's related. And once again, we're going to use the good old technique of KVL on the left-hand side and KVL on the right-hand side and see what shakes out. So on our left-hand KVL loop, we're going to wind up having, let's see, so KVL at our left-hand side of the circuit. We are going to have VTH will be equal to our Thevenin resistance times our base current IB plus VBE plus our emitter resistance times IE. So this is literally the first time that IE has shown up in any of our equations because it's the first time we have a resistor there that a voltage drop is going to occur, right? So our base current and our emitter current can both be expressed in terms of our collector current. So let's go ahead and do that, right? So our base current is just IC over beta. So that's going to look like RTH divided by beta times IC plus VBE. And then our emitter current should be beta plus 1 over beta times our collector current, if memory is serving me correctly. All right, so just as a quick aside thing here, I believe we have IC, and then our base current is IC over beta, and then our emitter current is IC plus IB. So that's going to be 1 plus 1 over beta, which is the same thing as beta plus 1 over beta times IC. So here we'll have RE, beta plus 1 over beta IC, and we can just lump these IC terms together. So that's going to look like RTH plus RE times beta plus 1. All of this is divided by beta times IC plus VBE. And then we could express IC in terms of VBE or VBE in terms of IC just using our standard relationship. And we have a one equation, one unknown system. If there is no early effect present, if there is an early effect present, then we're going to have a dependency on VCE here as well, which means we need to definitely write a KVL equation around our right-hand loop. So on the right-hand side, we're going to have VCC is equal to RC times IC plus VCE plus RE times IE. And once again, we're going to express IE in terms of IC so that we have the least number of variables. So that's going to be RC IC plus VCE plus RE times beta plus 1 over beta IC. And then just grouping things together. Let's look at this as RC times beta plus RE times beta plus 1, all divided by beta IC plus VCE here. So now we have our two equation, two unknown system that we can solve in the case of an early effect. Yes.
Where did the data look?
So I have RC and then I'm just saying beta over beta. So that's just a 1 so that I can lump everything together in the numerator. Yep, that's it. Just me trying to make it look pretty. Any questions about my algebra or anything here? All seems fairly straightforward. Okay, so all right, so the last possible type of biasing circuit that we could see is what's called the self-biasing network. You know what? I'm going to actually do this on a completely separate page. Not that it's going to take a ton of space, but all right, so in the self-biasing network, we're going to have something like this. So here's our supply voltage VCC. Here is our resistor RC. And there's the remainder of our network. Let's see here, defining all of my currents and all of that kind of good stuff. Actually, that's a mistake. So that's IC right there. Here's IE right here. Here's IB right here. So if we were to apply Kirchhoff's current law at this node, the current flowing down through RC would be equal to IC plus IB, which is just what? IE, the emitter current, right? So we actually have an emitter current flowing down here that splits off to form our base and collector currents and then recombines to give us our emitter current down there. Here's our voltage VBE. Here's our voltage VCE. So before we get into detail with the math, what's the purpose of the self-biasing network? Anybody have any thoughts on what's going on here? So how are VCE and VBE going to compare to each other with this particular network? So I believe that VCE will always be greater than VBE because if we did KVL around this outside path, or actually, so VCE is the potential difference from here to here, right? So from this point to this point, which by definition is going to be IBRB plus VBE. So our collector emitter voltage will always be higher than our base emitter voltage, which means this particular configuration will always give us operation in the forward active mode, right? Assuming that RC isn't so large that VBE is so small that the device doesn't actually turn on and do anything, right? That's the limitation there. We can choose RC so large that we don't actually get a lot of current flowing through the device. Okay, so from this, let's throw some math at this guy really quickly. So we have KVL on the left-hand side. So that's going to look like VCC is equal to RC times IE plus RB times IB plus VBE. So that's going to be RC times beta plus 1 over beta IC plus RB over beta IC plus VBE, or RC times beta plus 1 plus RB, all divided by beta IC plus VBE. So there's one equation where the only unknown quantity is could be expressed in terms of either IC or VBE. And then KVL on the right-hand side is going to give us VCC is equal RC IE plus VCE, or RC times beta plus 1 over beta IC plus VCE. We can solve for IC, VBE, and VCE using this system of equations. All right, so anybody have any questions about these biasing networks? Yes. To ensure that it is literally impossible to knock this thing into saturation. That's it. And realistically, they're not used practically ever. We've used a 4 resistor network or the resistive divider biasing network and just design it so that we give ourselves enough headroom so that we don't actually knock it into saturation mode. We'll see. So this particular connection here, especially or more frequently when dealing with MOSFET transistors, is what's commonly referred to as a diode connected transistor. So let's explore that really briefly here to understand why. Okay. So if we were to draw the large signal model for this thing, and just the part that I have circled here, And I hope this shakes out the way that I think it's going to, but it'll be okay-ish if it doesn't. So here's our base. We have our diode between our base and our emitter. Here's our current source. That is IS EXP VBE over VT. And then up here is our collector term. So between the collector and the base, we now just have this resistor RB. Doesn't look as pretty as when we do it with a MOSFET, where that's just literally going to be a short circuit. Yeah, this isn't going anywhere, to put it bluntly. For a MOSFET, it turns out looking really, really pretty, and effectively what we're gonna see is that the voltage drops here and the current here are linear related, so that we can actually just treat the thing as if it were a resistor. But because we don't have a short circuit here, it makes it a little uglier and doesn't really help what I'm trying to explain. So let's just throw that away and we'll come back to it when we deal with MOSFETs. My bad. Like I said, worried it wasn't going to come out okay, and it didn't. But anyway, so this is commonly referred to as a diode connected device. And from a small signal perspective, it winds up just looking like a resistance. All right. So now let's talk about the PNP BJT. This should go relatively quickly because I believe at this point we have a pretty firm grasp of how the NPN BJT works. So let's start our discussion regarding forward active mode operation. And hopefully you guys recall from when I first introduced the concept of bipolar junction transistors, for the PNP BJT, effectively we have the exact same sandwich structure except that it's reversed. So we'll have P-type and then N-type in the middle and then P-type. And we want our emitter to be at the point of highest electrical potential, which is exactly opposite what we saw for our NPN BJTs, where the emitter was at the lowest point of potential, okay? So effectively, we're going to have positive charge carriers flowing down through the device, giving us a positive current, whereas for NPN BJTs, we had negative charge carriers flowing up through the device, which gives us a positive current flowing down, okay? All right, so drawing this guy out, this is our very heavily doped emitter. Here we have our base that is heavily doped, but not doped as heavily as the emitter. And then down here, we have our collector, which is doped P-type, like so. Here is our collector terminal, okay? This is our base collector junction. This is our base emitter junction. And so we are going to put a voltage source between our emitter and base to control whether the base emitter junction is forward or reverse biased. So this is going to be our voltage VEB. And then we're also going to put a voltage source between our base and collector to control how that particular junction is biased. And this will be VBC. So just as an inkling of what's to come, effectively we have an incredibly similar situation of what we saw with the NPN BJTs. The only real difference is that the subscripts on our voltages are the opposite of what they were previously. Okay. So if we want our base emitter junction or our emitter base junction, whatever way you float your boat, to be forward biased, does VEB need to be a positive voltage or a negative voltage? Positive voltage, right? So VEB needs to be greater than 0. And when VEB is greater than 0, we are going to see that the barrier potential of the base emitter junction is lowered such that a large number of holes can diffuse across the base emitter junction. And similarly, the majority carriers in the base, which are electrons, will be able to diffuse across the base emitter junction into the emitter region. Since there are way more holes diffusing down than there are electrons diffusing up, we should expect to see that we will have a positive emitter current flowing down because of this situation. Right? All right, so now let's look at the base collector junction here. For this to be forward active mode, our base collector junction needs to be reverse bias. So should the voltage VBC be positive or negative? It should be positive to reverse bias this junction. So when our base collector junction is reverse biased, we are going to have a relatively large electric field capable of sweeping our minority carriers in the base region through down to the collector. We should also see some small amount of recombination. So something like this. So these are still our holes. Since this junction is reverse biased, the majority carrier electrons in the base should be repelled by the strong electric field. So we should not see diffusion of electrons from the base into the collector. So our collector current is only dependent on those holes. So here's IC, just for the sake of argument. Let's put ground down there like so. And then the purpose of our base terminal is effectively to supply electrons for diffusion into the emitter, as well as to recombine with our holes in the base. So since the electrons are flowing this way, our base current should be flowing in the opposite direction. So our base current flows out. So we can see that IC plus IB still equals IE, even though all of our currents are flowing effectively in the opposite direction as they were previously. Our collector current IC is going to be IS times the exponential of VEB over VT now. So effectively we're saying it's whatever our saturation current is for this junction multiplied by the probability of holes diffusing across the base emitter junction is. Our base current will once again be IC over beta. So that'll be IS over beta times the exponential of VEB over VT. And our emitter current is then going to be beta plus 1 over beta times IC, or beta plus 1 over beta IS exponential of VEB over VT. So those are all of our relationships. Early effects while we're at it. So what's the early effect going to do here, right? So as this junction becomes more and more reverse bias, this effective width is going to get smaller, which means we should see our quantity IS gets a little bit larger, which means we should see all of our currents increase yet again, right? So effectively, I'm going to put this in a different color here. With early effect present, we should then simply just introduce this term, where instead of being VCE, it'll be VEC over VA. And then we can put that there and here as is needed when early effects are present. So it's the exact same relationships that we had for our NPN BJTs, except that we just swap the subscripts. That's literally it. Our large signal model so here is our schematic diagram representation. Here's the emitter, base, and collector, where this is the direction of our, let me put it down here. Here's IB, IE, and IC. This is our voltage VEB. This is our voltage VEC. Large signal, we're going to have something like this. So here's our base. Here is our emitter. Here is our collector, like so. This will be the voltage VEB. IE, IC, and IB. Bless you. And then small signal. Actually, yeah, we can call it VEB, VPi, whatever the hell we want to. Doesn't matter. It's the same thing. Where this R naught right here is due to the early effect. Close. So if the early effect was not present, that guy would look like an open circuit, and we would effectively just have the exact same small signal model that we had before. except it's flipped upside down, which literally changes nothing. So let me explain how much it literally changes nothing. If we were to call this voltage VBE, what would we do? We change the polarity of this voltage, which would in turn change the direction of this current, which would give us literally the exact same small signal model as an NPN BJT. So these small signal models are literally interchangeable. They are the same thing. I typically draw the small signal model for a PNP BJT upside down just because that's how I learned to do it, but it doesn't hurt anything to draw it just like the other. Everything works out literally exactly the same. All right, so we're done with BJTs. Unless you guys want me to talk more about BJTs. Yes. Are not. So yeah, and it is the same exact equations that we used for NPN BJTs. So it'll be VA over IC, if my memory serves me correctly. Guess I could probably look. No, I didn't bring those notes to me, but anyway, the exact same equations as before for calculating our transconductance and calculating R pi and calculating R naught. Literally the same relationships. EB right here, EC right here. All right, so over our brief break here. Oh, actually, let me pop onto Canvas real quick. I don't know how many, if any of you guys have noticed. There's my mouse. All right, so the first thing I want you all to notice is that your take-home portion of your exam has been posted. It is due next Wednesday, I believe. So I think that's plenty of time yet, 17th. There are 3 questions. Let's open it up and look at things here really quickly. That's the wrong thing, but we'll talk about that in a moment. So the first question is, I give you 3 different theory questions that will require a bit of explanation. Pick 2 of them and explain what I want. Okay. Tell you very explicitly that if your explanation includes materials obtained from external sources, cite the sources. If you don't cite it, then that's bad news. You get a 0 on the whole damn thing, and I file an honor code violation. I fully expect you guys to look stuff up on the internet. Just tell me where you did it. Okay. IEEE format. I mean, just tell me what resources you use. I don't think you need to cite my video lecture because that's material from the class. So if it's external to the class, meaning from a textbook or a Wikipedia article or a journal article or something like that, do that. But it's literally from, if you're regurgitating bullshit from me, I don't think that needs to be cited. Problem 2 is a design-ish problem, in as much as I'm giving you just parameters for a made-up semiconductor, and then your job is to design effectively a diode under the following constraints. NA and ND, so your doping concentrations for your acceptors and donors, must be greater than the intrinsic carrier concentration by a factor of at least 10. The built-in voltage of the junction can't be greater than half a volt, and the unbiased depletion capacitance needs to be at least 1 femtofarad. You get to decide what the area of the junction is, but don't make it some asinine thing like it's a meter squared or something like that. Be realistic, right? So I would argue the largest you could realistically do would be on the order of 5 millimeters by 5 millimeters, and that would still be huge. And then based on whatever you get, I want you to tell me what the capacitive tuning range of the device is going to be for reverse biases, voltages ranging from 0 volts to 5 volts. So that is problem 2. And then problem 3 is that I want you to complete one of the design prompts found in your design project thing, which I also uploaded, as an individual project. And then I have a note here that says, whichever project you choose to complete for this exam cannot be completed by your degree. So let's now look at the design project assignment thingy, just really quickly here. I'm trying something new here. I have it set up to where you guys can define your own groups. So it can be from 1 to 3 students. And I'm not entirely sure how it works because I can't, as a test student, when I go into the student view, it tells me all the groups are locked, but anyway. So there are 3 different projects and I want you to complete 2. Now, I want to be clear about this because it might be worded oddly. You don't do, if you're doing project 1, you don't do 1A and 1B, it's just one or the other. Okay, so either you design a single phase rectifier circuit that takes your 6 volt, 60 hertz input signal and converts it into a 5 volt DC signal with a ripple of half a volt, or you do this guy where it's a 3-phase input signal, converting it down into a 48 volt DC signal. I should have subscripted that. I'll fix that later and all that kind of stuff. So first project is a rectifier circuit. Choose your own adventure, whether it's a single phase rectifier or a 3-phase rectifier circuit. Second project is a voltage regulator project. So it's either a 5 volt voltage regulator delivering 5 watts of power. So that would be something like the voltage regulator you would see for an Arduino or a microprocessor or something like that. Or a 48 volt voltage regulator for delivering 300 watts of power that would be used in a telecommunications system because they regularly use 48 volts DC for their systems or whatever. So this would be like a voltage regulator for a radio transmitter. Project 3 is logic circuits. So either a 3 input AND or a 3 input OR, where your input signals are 1.8 volts is a logical 1, 0 volts is a logical 0, rise and fall time of 5 nanoseconds. And then for the output to be considered 1, it needs to be in the upper third of that range. For the output to be considered 0, it needs to be a lower third of that range, which means you're going to have to choose diodes that have small on voltages so that you can meet those criteria. I also give you a note that since our transients here are on the order of nanoseconds, you need to make sure that your simulation time step is small enough to capture those transients. So if you can't see them because you were lazy, that's not my problem, right? So you should see something. So AND gate and then the criteria for the OR gate are literally the exact same. So just to clarify things here a little bit further, let's say that you as an individual decide to do project 3A. That means your group can't do 3A, but it could do 3B or something like that. So I don't want it to be such a huge nightmare of finding somebody that didn't happen to do the same thing as you did and all that kind of stuff. So the due date for the take-home exam is next Wednesday. The due date for the design project is the end of the quarter. So, all right. And then over the break, I'm gonna work on a homework assignment, just a single homework assignment for BJTs that will be consisting of, I'm gonna give you some BJTs with voltages present at the different terminals, and you need to tell me what state it's in. So whether it's forward active, reverse active, cutoff, or saturation, and then a couple of problems with bias circuits, including and not including early effect as I see fit. Then we're going to do effectively the exact same thing for MOSFETs. And you'll have one homework assignment on MOSFETs, and then your exam will literally just be a bunch of bias circuits that you need to analyze. All right. Any questions, comments, concerns, etc.? All right. Have a good holiday break. I hope the weather doesn't get bad till Tuesday so that we actually get a snow day. Because I hate it when the weather gets bad on a day we're already off. It's such a waste.